But I'm going to show a method we developed very recently in our labs. I'm part of the CHOSE lab at the University of Rome, where we're mainly working on perovskite solar cells, but also on other new generation photovoltaics and biohybrid devices. So I'll just go through an introduction on perovskite solar cells, why flexible, what is anti-solvent engineering, and then go on to show the method and the results, finishing with conclusions and some ideas for further work. So perovskite solar cells are solution processable, and you can deposit them through a precursor ink. And the main technique is spin coating, of course, in the labs. Then you dry and you knead it up around 100 degrees, and it converts to the final perovskite layer. This is methyl ammonium lead iodide, and this crystallization process is key to obtain high efficiency solar cells. And you can go flexible by using substrates like PET, but also even paper or other types of devices. Flexible, of course, is also appealing for roll-to-roll deposition. And there's a lot of applications for flexible, from building envelopes to what we're seeing here a lot. I mean, perovskites have been shown to give very high efficiency indoors, so they could power some of the nice sensors we've seen during this conference. So perovskite solar cells, since 2009, where the initial efficiencies were 3.8%. Now the record are 25.7 at standard test conditions. And flexible solar cells started a bit later, but they've also reached very high efficiencies, which are now 22%. And the key, as I was saying, is the crystallization and the conversion from precursor to the final perovskite layer. And most high efficiency cells use what is called anti-solvent engineering. So you start the spin coating of the precursor ink, and after about 25 seconds, you add an anti-solvent while it's spinning. The anti-solvent helps move away the original solvents, but doesn't dissolve the precursor materials. And it helps not the nucleation, but the growth of the crystals. So you can achieve better uniformity and larger crystals. However, when you go to roll-to-roll compatible large area techniques, anti-solvent isn't really applicable. So they use drying or heating, and this is engineering. So this is the device structure we've been using. So polyethylene terephthalate substrate, then ITO. This is SNO2 layer where you can inject electrons, but it blocks holes. Then the perovskite layer where the photo absorption happens. There's a HTM spirometad where it collects holes, but there's a barrier for electrons. So this is the standard structure for flexible cells, and these are all at low temperatures. And this is the final cell photograph of the side, final cell. So what happened is Nazila Zarabinia, who's the first author of this paper, she came to do an internship in our laboratories from Iran, and she was actually working on slot die coating. But she came on a meeting to me and she said, look, I deposited a tissue after scraping away the spirometad, which is actually an anti-solvent, and I left it there. When I took away the tissue, I saw the perovskite turn brown. So I suggested she stop everything and develop a method in the last 2 or 3 months of her stay, using actually these soft applicators to deposit the layers. So this is what we did. So we applied PET ITO SNO2 on a hot plate so we could control the temperature. And it was taped on with 50 micrometer tape. We applied the perovskite solution, and then we tried different applicators, soft applicators, including tissue, paper, you see polyamide, and we drew it over the ink, and at the trailing end, you'd form a film. Now, in one case, we'd apply anti-solvent on the paper applicator before deposition, because we thought this was going to be key. And this is just a cross-section of this method, but the best way to really show this manual method at the moment is to show a video. So we soak the piece of paper in anti-solvent, ethyl acetate in this case, apply the precursor solution, and this is soaked in anti-solvent. You draw it from one end to another. The hot plate is at this case 125 degrees. So it helps the conversion of the perovskite, and it's compatible with a plastic substrate. And you see here at the trailing end, it's converting into perovskite. And the drawing speed is about 0.1 centimeter per second. So as I said, we tried different soft applicators. This was the tissue which we started with, polyamide. Tissue absorbed most of the precursor solution, so nothing was left on the substrate. Polyamide isn't absorbing enough, so it wouldn't help in forming a nice film. Piece of dry paper, you get nice thick films, but not very uniform. And by first soaking the paper in an anti-solvent, not the solvent, but the anti-solvent, you get better films macroscopically. Also, we did a study in which temperature was best. Now for PET, you can only go up to 125 degrees, otherwise they deform. And actually 125 degrees, again, macroscopically, the film uniformity was better and compatible with plastic substrates. We then did, more microscopically, high resolution microscopy. This is SEM. So this was drawing with a normal piece of paper, and here it was drawn with a piece of paper applicator soaked in anti-solvent first. You can see here there's some cracks, much more uniform with the anti-solvent. And also here you can see that nice crystals are uniform throughout the thickness of the layer. So it helps the charge carriers go from one end to the other without encountering too many grain boundaries, which of course act as recombination centers. So the morphology certainly improved. We carried out XRD, and the full width of half maximum goes from 0.36 to 0.8 in the 100 direction, which means higher crystallinity for the anti-soaked applicator, the films made with the anti-soaked applicator. And also the composition looked better because we used the bicomponent perovskite, and the black phase, which is photovoltaic active of cesium lead triodide, had a more intense peak. And these were the best cells, the JV curves of the best cells using a dry applicator and one in anti-solvent. You can see the efficiency goes from 6.8% on PET to 11.1%. So almost doubling by just soaking. And this is a manual technique. And this is the histogram showing the reproducibility. So 11% here, 2/3 of the samples, which were 40, were 8% or above. So surprisingly good reproducibility for just a manual process. And these are PL experiments which show that there's less defects when you use the anti-solvent soaked applicator. the fall time of the VOC is much longer. And we also carried out some simulations which show that the defect density is greatly improved when you soak the soft applicator in anti-solvent. Goes from 8 to 3 times 10 to the 16 centimeter to the -3. And so in summary, I've shown a new method that uses a simple sheet of paper to deposit the perovskite film. Paper compared to other soft applicators possesses the right porosity and smoothness. The trick is to soak the paper applicator in anti-solvent. 11% efficient cells can be used. What are the possible future developments? One is to automate the deposition, maybe use a slot die or blade coating head with this trailing soft applicator where you apply the anti-solvent, so no need for drying or through airflows or high temperature heating, and maybe extend it to all the other layers, which for some laboratories who are just starting or don't have the money for high cost equipment, this could be useful. And also for people who do have equipment, it's a new way to help crystallization. This is my last slide. We showed the first perovskite solar cell on paper. And here the trick was using some transport layers which were compatible with paper substrates, and a top electrode which was transparent, made with molybdenum oxide, very thin gold and molybdenum oxide. The initial efficiency was 2.7%, but paper is recyclable, low cost, and in a way skin biocompatible. So we could think of using paper not only as an applicator, but as a substrate material. With this, I thank Nazila Zarabinia, the main author of this paper, student in my group for 6 months, and the funding agency, and you for the attention.